right, in lesson 15b, we're continuing with semi-log plots. Said in the first lesson on semi-log plots, we knew the base of the exponential function. But if we have real-world data and do not know the function of the base, we will take the logarithm of the output values, and then we can graph using a logarithmically scaled vertical axis. So, whether we have the exponential function of raw data, in either case, we can linearize the data by transforming the y values to a logarithmic scale. All right, so here it says we're going to use the table below. The table below gives the values for the function f of x and selected values of t. A says we're going to graph the data on the semi-log plot on the following slide, which yours is right there next to it, and label your axes. B says we're going to, what does the graph say about the data? And C is approximate the values of f of 3 and f of 9 using the graph. All right, so let's look at the next slide here. So we're going to graph these points. All right, so we got the points with 0 and 0.3, which I don't have on here, I can't do. Let me label real quick one thing about it. So this is going to be my x, and these over here, this is going to be my f of x. All right, 2 and 1.2, that's not, yeah, I can graph that one. So 2 and 1.2. Then we have 4, 5.8. 5, 12.6. Now what's your scale? Because remember, this is 10. And then up here is 10 squared, which is 100. Okay, so these are all by 10s right here. So watch out for that. So let's see. Was it 5 and 12.8? All right, 6, 28.8. 7, 65.4. 8, 156.2. 10, 820.3. 12, 5342.6. So 5,000. So a little more than 5,000. And 13 is almost 10,000. All right, we can see there it does appear that it is linear. Okay, now remember this is estimating, so it could be off a little bit there. To keep going in that direction. All right, so question B, instead of going back to the other page, says what does this graph say about the data? So the graph appears to be linear. On the semi-log plot. So the data is exponential. All right, so exponential data will appear linear on the log plot. And it has to do with the fact that exponentials and logarithms are inverses of each other, and they are reflections across that line y equals x, which is linear, okay? All right, then C says approximate the values of f of 3 and f of 9 using the graph. So f of 3, I'm going to change colors here. Go to where x is 3. Points right about there. So I don't know, somewhere between 20 and 30. Looks like a little closer to 30. So how about 28? I'm sorry, not 28, 2.8. Excuse me, between 2 and 3. Watch your scale, just to prove my point. And then f of 9 right in there. So between 300 and 400, so maybe about 350-ish. Okay. As long as it's between 3 and 400, you're good, okay? All right, example 8. It says the table at the right shows a bacteria population in thousands in the culture at a time of T hours. Make a scatter plot of the data. What does the shape of the plot suggest about a regression model to fit the data? All right, so if you take and you put your time in L1 and your bacteria in L2, and you go through and you run your scatter plot. So remember, you do your stat edit, put your information in. Then you're going to go to second, y equals, turn on plot 1. Your data is in L1 and L2. And then go to zoom. And it's the one that says stat. So I think that's what, number 9? Yeah, number 9. So zoom stat. Okay, and you'll be able to see those points, and it's going to appear like this, which you can tell then it does look like it's exponential. All right, to linearize the data, we're going to find x comma natural log of y and complete the table at the right. Now, if you're in your stat edit, let's go back to our stat edit. We've got our time in L1, our bacteria or our Y's are in L2. So go up on L3 and you're going to type in natural log. It's going to open a parenthesis and you're going to go get L2 by hitting second and the 2 button and hit enter, and it's going to fill in those numbers for you. And so you'll see that at time 0, it's going to be 1.831. Then it's 2.771, 3.750, 4.742, and 5.739. All right, C says to graph the linearized data and find a linear regression equation where y hat is equal to the natural log of y. So they showed us here, so see the image below, they went ahead and graphed it, okay? But you need to go run your regression data, and we want it to be linear. So you can go to your stat, calc, then your linear regression. Be careful, your x's are in L1, but your y's are in L3, so make sure you change that, okay? All right, and so what you should get then is your y hat is going to equal 0.979x plus 1.809. All right, D says use the regression model for the linearized data to find a model for the original data set. So now we're going to go backwards. Well, remember that we had just found that y hat was equal to 0.979x plus 1.809. But our y hat, remember, was our natural log of the y. So I'm going to change that back. Now, going back to, remember what we do to one side, as long as we do it to the other side, our equation is equal. Well, remember we had, like if I had natural log of e, because my little base was e, and this base is e, it was equal to 1, or so we could say that it canceled. We have the same thing when we're dealing with the logs up in the exponent. So if I have like e to the natural log of something, I'll just say x, then because this e and this little e that it has right there are the same, they will cancel each other out, and it makes that x become a full-size number, okay? And it's just playing with your logs. If you're unsure of it, then you can do your b to the y equals x, log base b of x equals y, and solve it and see that it works. But so what I'm going to do here is I'm going to take and I'm going to exponentiate both sides of this equation. So I'm going to take and make both of these equations, or both sides of this equation, the exponent, where both of them have the same base of e. So we have e to the natural log of y equals e to the 0.979x plus 1.809. Now we know, don't do this on your paper, but we know since our bases are equal, we could ignore our bases and our exponents have to be equal. All right, so but we're not going to do that. So now I can use this, what I talked about over here. I have e raised to the natural log of e. This e and this little e that's a base of the natural log are the same, so we can ignore it, and it'll bring out a full-size y equals. Now, on this other side, we're dealing with adding of exponents. So remember what makes us add exponents? If we have like bases. So this is the same as saying e to the 0.979x times e to the 1.809. Which so that I can make it look exponential, like y equals a times b raised to the x. I'm going to switch here. Order doesn't matter in multiplication. So this is e to the 1.809 times e to the 0.979x. And then we could actually just go ahead and work that out. So we end up with y equals e to the 1.089 is approximately 6.104 times e to the 0.979x. And so there is our model for the original data set. E says, use the equation that models the original data to predict the number of bacteria present after 12 hours. So we just want to plug 12 in for that. So we get y equals, or I'm going to do y of 12. I'm plugging in 12. Is the 6.104 e to the 0.979 times 12. And so we see that that is approximately 772,157.863 bacteria. Oh, and be careful, I missed it almost. I can't see mine at the top, but remember the table at the right shows the bacteria population in thousands. So this would be thousands of bacteria. Always watch out for that. All right, example 9 says the table at the right shows the amount of revenue R in billions of dollars collected by the IRS for selected years from 1970 to 2015. Consider how the revenue by year seems to change for each 5-year period. Is it changed by a constant difference or by a constant ratio, and explain? All right, so what we need to do, it's going to take a little bit here, is go through and find your differences, okay? So take your bigger number minus your smaller number and find your differences and see are they kind of in common. They're not going to be exact. This is based on real world data, okay? But they should be close. So you shouldn't have like where you're adding 20 or 30 and then where you're adding 1,000 or 2,000, okay? So they should be consistent. What I can see here just looking at this data is I don't see any real flukes so much, except between these two, 192 to 279, that's less than 100. And right here, this is more than 1,000. That's not going to be a constant difference, okay? So I'm not leaning towards constant difference. I'm going to check that constant ratio. And so the ratio, remember, is where we just divide them. So we would take our 279.1 divided by the 192.8, and I believe we get like 1.4 something, okay? And then 517 divided by 279 and get a number there. You take the 2150 divided by the 2030, get a number there. Those two are awful close together where the others aren't so I'm thinking that's going to that's going to give us some bad data in between those two. So don't just base it on that. But what you should see is most of these are kind of close. Okay, so some of them are like 1.4, some of them are 1.6s, some are 1.5 somethings. And so the ratio is a lot closer than the difference. So it's going to be a constant ratio. And I just picked around, kind of in the middle there, around 1.5%. Okay, I had some bigger, I had some smaller, just kind of in the middle there. All right, B said to find an exponential regression model for the data. The graph is shown below. All right, so we're going to put this in our sorry, my battery's getting low there. So we're going to put this in L1 and L2. Now, I didn't type in 1970, 1975, 80, 85. What I did is 1970 was year 0. So this was 0, 5, 10, 15, 20, 25, 30, 35, 40, and 45. So that's how I did it, to put them in my calculator. Put your revenue in L2. And let's go find the exponential regression model. So I'll run my exponential regression, and I get that it is 250.8639 times 1.06273 raised to the x. Now we're going to do something more with these numbers. So, and they mentioned these numbers later in the problem here, so I would use those numbers. All right, C says interpret the meaning of the 250.864. That is that A value, that is the initial value. So remember when we looked at, it's been a while, when we looked at this equation, this A right here was the initial value. It's when our x is 0. So the 250.864, this is going to be the estimated tax revenue in 1970. So the estimated tax revenue in 1970, because that was our year 0, is 250.864 billion dollars. D says interpret the meaning of the 1.06273 in the regression equation. That 1.06, that is the estimated growth rate. Okay, that's the rate at which it was changing. So the estimated growth rate of tax revenue in billions of dollars per year is approximately 6.273%. Okay, well, so what we did here is we took out the 1, because the 1 is the previous year's amount and how much it's going to grow after that, okay? So the actual growth is, you take out the 1, you get the 0.06273, and then to change it to a percent, I just had to multiply that by 100. Okay. E says use the exponential model to predict the tax revenue for the year 2025. So 2025, if 1970 is year 0, then 2025 is going to be year 55. And so we're just going to plug this into our equation. So the 250.864 times 1.06273 raised to the 55. And so we can see that is 7,123 point. I'm going to put a bunch of decimal places here. Because remember, this is billion dollars, okay? So if you multiply that by a billion, all those numbers all of a sudden become really important. F says the data modeled by an exponential function can be linearized by finding x, comma, natural log of y. Complete the table below, round your answer to the nearest tenth. All right, so we're just going to take the natural log of the y. Now, you put all those numbers in your L1 and L2, didn't you? So let's go back into your stat edit, and over here on L3, let's add in the natural log of L2, and then hit enter, and it's going to give you all of that data. All right, so for 0, I'm just going to round it to one decimal place. It tells me 5.3, 5.6, 6.2, 6.6, 6.9, and we just keep writing it down. If If you notice here, there's no change here, but that 35 and 40, that's where we had that small difference in those y values. Remember I said it's kind of bad data right there? I mean, it's not really bad data, but it's not continuing with the pattern of what was going on the other years, okay? So that's why that's showing the same. And then G says a graph the linearized data from the table above. Find a linear regression equation where y hat is equal to the natural log of y. All right, but they didn't give us a graph, so we're just going to graph it on our calculator and look at it, okay? And so we're just going to do our linear regression equation. So we're just going to run linear regression using L1 and L3, and we should get 0.06084x plus 5.5249. Remember, it's just linear regression using L1 for your x's, L3 for your y's. All right, and then actually when you graphed it, that should be what your graph looks like there. So H says the linear regression equation for the line shown in the image at the right is what we just found. How are the numbers in the transformed linear model related to the numbers of the original exponential regression? So we're going to interpret the meaning of the 0.060848 for the linear regression equation. All right, so that was the slope of our linear regression equation, okay? So that's how it's going to increase or decrease. It's positive, so we know it's increasing. So the natural log of tax revenue per year is estimated to increase by that 0.060848 billion dollars each year. Interpret the meaning of the 5.53091. Well, that's our y-intercept. That's at year 0, which was in 1970. So the estimated natural log of tax revenue per year in 1970 is the 5.53091 billion dollars. All right. It says use the linear model to predict the tax revenue per year for the year 2025. So in 2025, that's the same year we used earlier, so we know that it's going to be 55 years later. So I'm just going to plug 55 into my equation. And that gives me approximately 8.8711876 billion dollars. All right, replace y hat with the natural log of y and solve for y. Will this new equation give the same prediction for 2025? So we know that this is just the natural log of y is equal to our equation. And so we're going to do like we did earlier. So in order to get the natural log and the y away from each other, if I exponentialize it, same thing if I did b to the y equals x, guys. If I changed it to exponential form, I'd get the same exact thing here. It's just a little less writing. Okay, and so it's equal to this other side, and I'm going to split this because they're being added. I know that means they had like bases, and they were being multiplied with like bases. So this is e to the 0.0608481x times e to the 5.52491. And so I get y equals, I'm going to take this part and write it first. So e to the 5.52491 is approximately 250.863991. And that's times e to the 0.0608481x. All right, and then if I want to prove it, all I have to do is plug in that 55 again and make sure I get the same answer I got earlier, and you will. All right, example 10 says, will this method work with log base 10? The following table shows the population of a city over time. Create a semi-log plot of this data and interpret the plot using the y hat is equal to log of y. A says find a linearization of the data where y hat is equal to log of y. So we're going to go through and we're going to find our natural log equation, natural log of y equation. I'm sorry, not natural log, log of y equation. So I'm going to go through, I'm going to put this in L1, but I'm going to use 0, 5, 10, 15, and 20. I'm going to put this in L2, and I'm going to go in L3 and type in the log of y and let it populate that for me. All right, when I do that, I get these numbers. All right, and then I want to find my equation. So I'm going to go to Stat, Calc, Linear Regression, L1 and L3. And I find that it's y hat equals 0.01496x plus 0.31481. B says explain the meaning of the slope and the y-intercept. All right, so the slope is positive, so we're increasing. So the log of the population is estimated to increase by that number per year. So the log of population is estimated to increase by 0.01496 million per year. All right, the y-intercept. Remember, the y-intercept is when your time is 0, so that's the year 2000. Okay, so the estimated log of population in 2000 is the 0.31481 million. All right, and C says what is the predicted population for the city in 2035? So we're just going to go plug in 2035, which 2035 would be where T would equal 35. All right, we'll work that out. And I get 0.838535. But now remember, now this is the y hat of that, which is the same as the log of y, okay? So then to solve for y, I change it to exponential. So b to the y, my base is 10. My y is that decimal equals the x, which is my y. And so I get 10 to that number, which when I type that in, I get about 6.895 million. All right, in example 11, it says create a semi-log plot of the data and interpret the plot using y hat is equal to log of y. For 1980, use t equals 0. Find an exponential regression model for the data. So this is going to be your 0, 2, 10, 10, 11. So I'm going to go through and label these. So I'm going to use those for my L1. Put the salary in my L2. And if you want to, because you know we're going to have to do it, go ahead and do L3 and put in your log of L2 into that, okay? So then for 1980, okay, so we do that. It said find a exponential regression model for the data. So we're going to run exponential regression using L1 and L2. And so we do this, we should get y is equal to 1.21178 times 1.13459 raised to the x. B says to find the linearization of the data where y hat is equal to log of y. All right, so we know that y hat, or I'm going to put log of y since we labeled the other one y hat. And now I'm going to run my linear regression using L1 and L3 because that's where my log stuff is. And so I get 0.05484x plus 0.08342. C says explain the meaning of the slope and the y-intercept. So the slope is the log of salary. My slope is positive, so it's increasing. By the number, so 0.05484, and it's in millions of dollars per year. All right, y-intercept. Remember, y-intercept is at year 0. So the estimated log of salary in 1980, which is our year 0. Is $0.08342 million. D is what is the predicted superstar salary for the player in 2010. So 2010 is going to be 30 years later. Alright, so we know that the log of y is going to equal, we're going to plug 30 into that equation, and that's going to give me 1.72862. Now, earlier when I did this, I changed it to b to the y equals x. I can do that again, or I can use that exponentializing both sides of the equation. So this time, it's a log, which has a base of 10, and so I'm going to, I'm going to take both sides and make them the exponent on the base of 10. So 10 raised to the log of y gives me y equals, and then I just have 10 to the 1.72862, which is approximately $53.533 million. And then E says replace y hat with log of y and solve for y. Will this new equation give the same prediction for 2010? So we have log of y, do the same thing we just kind of did, equals our equation. All right, I'm going to exponentialize both sides, so just like what we just did there. So it gives me y equals, this is going to give me 10 to the 0.05484 x times 10 to the 0.08342. And I'm just going to put this part first. So we end up with y equals 1.2117695 times, and then I'm going to go ahead and work out this 10 to the 0.05484. That gives me 1.1345927, and it's just raised to the x then, because I worked this out, okay? I got a number for that one. And then it wants us to check. It says, will it give the same prediction? So we're going to plug in when y is, we're going to plug in x is 30. So when I plug it into this equation, I end up getting y is equal to 53.5327. Earlier we got 53.533 million. That is close. So yes, it gives us the same result. Our same prediction. All right, and that is the end of lesson 15.